Thank you. So good evening, everyone, and welcome to the last of our Retrofit for the Future sessions for this season. My name is Vicky and I work in the climate response team at Medway Council. This is the second year that we've worked in partnership with the University of Greenwich and Kent County Council to bring information sessions to residents and homeowners in Kent and Medway on how to make their homes more energy efficient. The intention of the events has been to provide impartial advice and information to empower attendees to make improvements to their home that best suit them and their property. We understand that each home is unique and there's not a one-size-fits-all solution when it comes to making your property more sustainable. The content of this particular session has come about because during previous events, attendees expressed an interest in finding out more about whole life cycle assessments and their role in reducing building-related carbon emissions and improving the efficiency of a building. So whilst tonight's event is aimed at helping you individually, it also supports the Council's aim to achieve a reduction in carbon emissions across Kent and Medway. Medway's homes account for over 40% of Medway's carbon emissions. Collectively and individually, we can make the changes necessary to reach our targets and address the climate crisis. So we do thank you for attending tonight. So without further ado, I'd like to introduce you to tonight's presenter and speaker from the University of Greenwich. Dr. Walsh is an interdisciplinary environmental scientist, having worked in areas as diverse as sports science and naval architecture. He works within the areas of resource and carbon accounting, life cycle assessment, and techno-economics. Prior to joining the university, he served as a research associate and fellow at the Tyndall Centre for Climate Change Research, based at the University of Manchester. He's undertaken life cycle assessment studies for commodity value chains, such as cotton and palm oil. And more recently, he's led a DEFRA-funded life cycle assessment project involving Rothamsted Research, which is a world-leading research centre. I hope I pronounced that right, Conor. University of Surrey and London South Bank University. And this project involves undertaking a life cycle assessment of a food basket of a range of different commodities. The project demonstrates important trade-offs in terms of competing interests, such as reducing the environmental burden and increasing the animal welfare of specific livestock systems. We hope you find this information useful and the session useful. I'll now hand you over to Dr. Walsh. Thank you, Conor.
Thank you very much, Vicky. Good evening, everyone. As mentioned, my name is Conor, and just as we start, I'd like to suggest that as we present, if folks have any particular questions, please put them in the chat. After which we will pick out some of the relevant questions from the chat, or you can just join in any face-to-face questions at the end. Now, this is the point in the iTunes installation process where you tick the terms and conditions at the end. So as Vicky mentioned, I'm a interdisciplinary research scientist, but I don't actually work in the built environment area. I'm just very interested in it, and I think it's a very important both enabler and also potential barrier to sectoral decarbonisation. So I'm really interested in it. So this talk is really just an overview of some of the types of questions that are posed within the built environment area. Specifically, this talk will be based around trying to introduce life cycle assessment, introduce whole life cycle assessment very briefly, and go through some case studies that have different research aims and provide different insights that are of relevance to trying to balance the need to reduce our collective environmental impact, but also provide services for people who need homes or places to undertake their business. So you're also probably asking, what's that strange picture there? Well, this is the Ahad Gate in the north of the ruins of Navinna, which used to be the capital of the Assyrian Empire, built about 6000 BC. Not very nice folks, these. The reason I've chosen this is because this particular gate incorporates two elements. Wood-fired brick that is still standing after being produced several thousand years prior, but also modern restorations to try to ensure its structural integrity, and unfortunately has since been destroyed by our friends in ISIL. So I think it's worth reminding ourselves that the built environment incorporates, in some instances, many, many important legacies of human development, which can be added to as we go on, but can be removed and destroyed very quickly. So without further ado, so this talk has three main aims. Sorry. I'm going to introduce life cycle assessment, briefly introduce whole building life cycle assessment. We're going to talk about some of the potential applications of these within the environmental and built environment areas. And we'll comment on how the application of some of these case studies can highlight the strengths and limitations of life cycle assessment. So, what is life cycle assessment? Well, before we start, I'd just like to ask a question, and we're not going to answer it right now, but just bear it in mind. Is it better to reuse or recycle steel? Steel is one of the most easily recyclable uh, materials available, or at least in terms of the maintaining its physical quality. So it's the choice of how we use steel at the end of its life is very important, and we'll be returning to that later on. So this is just a little tease to something we'll be talking about later on. So please keep this in the back of your mind. Okay, so life cycle assessment is a standardized process for trying to follow the flow of materials and environmental burdens or emissions along the value chain up to a defined point. In effect, it tries to act as a ledger that quantifies the flows of materials into and out of different systems and different segments of a value chain. It can be used to compare goods, but also services. You can use it to compare the impact of producing a shirt or the impact of washing 100 shirts. It's been informed by a number of different ISO standards, which regulate the structure of a study, as presented by this diagram here, which we will be going into now. The first stage is arguably the most important. The goal and scope stage effectively is informed by what your study seeks to accomplish. Are you trying to look at the impact of intermediate products, finished products? Are you looking at the whole value chain, or are you just interested in individual segments? So, for example, I've recently been involved in a study on coffee farms that's based on agronomic performance. How much yield do you get for your fertilizer? And so, for that study, we've decided to exclude the on-site processing, and we just draw the line at the level of the field because we're not really interested in anything else. Once you've decided what your study boundary is, what's the main materials that you want to try to track in your study, you then need to decide, okay, what is the unit by which these environmental burdens are expressed? And this is something that is on paper very, very simple, but can actually be quite difficult, or in some cases easy to get wrong. The functional unit is in effect the metric in which impacts are expressed, and it's very important to be very clear about this because this then determines whether or not you can compare your study with an alternative version. So, for example, whether or not a particular commodity like chicken is chilled or frozen is very important, particularly as something may be frozen and then chilled, or something may be chilled without the frozen step. So understanding the transformation of the material makes it really important for in terms of being able to actually make sure you're comparing something that really is comparable, i.e. it interacts the value chain, or it interacts the economy, or it interacts with the consumer at the same point. For buildings, in most cases, these studies are expressed in terms of either a unit of floor or wall space, or perhaps in terms of the entire building. This diagram on the right demonstrates a example of a study boundary for a study looking at concrete reuse. The heart of a life cycle assessment is the inventory stage, and that is just in effect a collection of all the material flows into and out of each individual value chain stage. So it's what type of resources do we need, divided into resources from nature or resources from the technosphere. That means things that have been produced, that have been already undergone some transformation in the economy, such as energy or materials. And our outputs are usually divided into outputs that are of economic value. These are our products. They can be our main products or our co-product. So, for example, a farm might or a field might produce a main crop, but it might also produce residue that could be used as an input for compost. However, unfortunately, not all of the outputs of an individual stage are beneficial. Unfortunately, most of our activities will embody both greenhouse gas emissions, but also um, uh, materials that have a local environmental impact through eutrophying or other impacts. And we'll be talking a little bit more about this trade-off as we go. So what does this mean in practice? Well, it means trying to understand how your final output is dependent on a preceding number of transformations. And each of these can be looked separately and as an integrated whole, reflecting the fact that the output of the preceding step is an input to the final step. So wheat is a very important input to the making of flour. Flour is a very important input into the production of bread. And each of those preceding stages will have material and energy inputs, as we've seen, and will release emissions that have global warming and local environmental burdens. And so what life cycle assessment does is effectively keeps track of all of those flows and expresses them in terms of your final product at the end. Now, this is a little bit simplistic because many processes will have a number of different products that might have varying economic value. Okay, so once you've done that, you can then effectively tabulate all these different emissions or all these different resource uses. But if you do that, you'll find them expressed in terms of several 100,000 different variants. Well, that's a lot. Uh, and most of us have better things to be doing than looking at different types of particulate matter. So but the way most life cycle assessment studies work is that they group different types of environmental burdens and express them in terms of a common unit of impact. The one you've probably all heard about is carbon dioxide equivalent, whereby other greenhouse gases, such as methane or nitrous oxide, are expressed in terms of their their carbon dioxide equivalent. So how much carbon dioxide has the same impact as 1 kilogram of methane. And we see similar equivalencies for other types of environmentally impactful materials, such as particulates, expressed in terms of a particulate matter of a particular diameter, or nutrifying, nutrient-bearing materials expressed in terms of their nitrogen equivalent, for example. One way I try to think about this, because it helps me look at and compare different studies, is grouping our impact categories in terms of whether it's global warming, which is a global impact, whether it is a local area impact or a human health impact, expressed here by the slightly brown shaded grouping of environmental impact categories, or whether the impact category is not an emission, but rather a resource use. How much water, how much land is occupied by this particular in the production and supply of this particular goods or service. Now, this is helpful, but sometimes it can be a little bit abstract. It might not mean all that much to people. So what we see here is what we term midpoint impact assessment. So we're not actually talking about environmental impact. This is a proxy. A kilogram of CO2 is not the same as the environmental impact. So different endpoint impact assessments effectively take all these flows as inputs, all these tons of or kilograms or grams of CO2 equivalent, and express them in terms of a unit of actual impact, be it reduction in species number or potential loss of human health. Okay, so what does this mean once we've done that? Well, once we've done that, then we need to try to interpret the results in terms of what kind of insights can we identify. But in order to do that, we first of all need to have a good understanding of the individual stages, the individual activities that are reflected first. So we see this particular diagram demonstrates the types of stages that might be relevant to a whole building life cycle assessment exercise. In doing so, we can try to identify, for example, what the most important hotspots are. If we look at this example, which we may or may not see later, which looks at the relative contribution of different stages reflected by different colors across different environmental impacts, we can see that the dark blue element at the top is very important for all impact categories, but ozone, the gray stage, is more important for ozone depletion potential than others. Okay, so one of the things that life cycle assessments teaches us is that sometimes the absolute value comparison is not as useful or is not as necessarily as insightful as looking at what the stages actually, the identifying the stages that contribute to this impact. Do we see the same sort of impacts, the same sort of activities contributing right across the board? For example, is there common hotspots for all the different environmental impact categories? Right. So how does that lead us to whole building life cycle assessment? Well, whole building life cycle assessment is a subsection of life cycle assessment methodologies that tries to apply these techniques to the entire life cycle of a building, from cradle to grave, or more accurately, from cradle to cradle, taking into account the production of the raw materials, their transport, the installation on site, the operation of the building, including any refurbishment, repair, renovation, and finally end of life, including the different waste streams that will be released or generated within the disposal stage, including looking at material reuse recovery. Okay. So in effect, this tries to apply, as we said, the types of the life cycle thinking to the very long functional life of a building. And what can that tell us? Well, we'll be looking at some examples that might be relevant in a while, but it can look at identifying the impact, for example, of different technologies with or without sources of energy. So maybe we are incorporating a different technology, but we're using the same grid electricity. Maybe we're looking at different types of materials that are replaced at different rates. And this can be used to try to inform certification or accreditation, like the BREEAM system. It can also help us identify economies of scale in terms of trying to allocate impacts in terms of a unit that can be compared across different building types. So is the impact per square meter higher or lower for a high rise or a single building, if we express things in terms of, let's say, floor space? So just an example, we can see this particular study that looks at the whole building life cycle assessment of a passive house in a subtropical climate zone. I have to say that's really pretty. I'm not sure about the paint color, but who knows? And what do the results tell us? So this study, I hope you can see this, but if not, I'll try to reiterate. This study looked at the impact of building materials, transportation, maintenance, recycling, etc., expressing it in terms of a unit of floor, a square meter floor space, and that was compared against other studies. And so this study demonstrated a higher embodied energy. So this is the energy embodied in the production of all the materials that were used in this particular building, but a comparable primary energy demand, that's the energy directly consumed on site, with other studies that are in similar regions. So the next study down, a passive house with photovoltaic demonstrated a similar energy consumption as the case study, but a much lower embodied energy. So this demonstrated that the choice of design had a trade-off in that the primary energy consumed of this was lower than other examples when expressed in the same unit, but might come at a cost of a higher embodied energy estimate. So, as we said, the results of a whole building lifecycle assessment can be expressed in terms of a unit of floor space or a based in the whole building, and that can inform the decision or help us decide whether or not the operational impacts are more important than those associated with material sourcing. And this is important because one of the criticisms of life cycle assessment is that it can be quite static. However, one of the benefits of whole building life cycle assessment is that it can accommodate a more dynamic perspective by having focusing on the impact of changes to the system, either changes in terms of the renovation, retrofit during the life cycle of the building, or changes to the background energy system that supports it. So whole building lifecycle assessment allows us this benefit of this comparison of impact in a unit that can be compared with other scenarios or other studies, whilst also allowing us to reflect the reality that during the entire life cycle of a building, lots of things can change. So very simply, this particular study is an example of some of the life cycle assessment, whole building life cycle assessment results. This is for a residential building in Canada based across a 60-year functional life. And we see our different impact categories from fossil fuel consumption, global warming potential, that's our CO2 here in the second column, and our local environmental impacts expressed on the right. And we can see an interesting trade-off in that the global warming potential is very much dominated by the operational energy, the heating, the cooling, which is perhaps not at all surprising. However, other local environmental and human health impacts, so the human health here is associated with things like particulates, is more influenced by the maintenance and the construction stage. So we do see this particularly for ozone depletion associated with things like the manufacturing of different materials. Oh, sorry, the maintenance and the manufacturing of different materials. So we can see this kind of trade-off between different types of impact categories that are more relevant to what happens before a building begins its operational life, and those that are more relevant to the operational life of a building. Right, so now we're going to move into our case study. So I'm going to speed up a little bit because we are moving on. Disclaimer number 2. No, I wouldn't necessarily consider all of these studies being exactly whole building life cycle assessment studies, and we'll demonstrate that in a while. In that, not every aspect of the entire functional life of the building is reflected within all of these studies, but they're chosen as they are reflect different types of research questions. Also, that means that as these reflect different types of research questions, the results themselves are specific to each study. While of course they can be compared, with similar studies, the comparability will be limited by their boundary, by their unit, by their assumptions. But all of these, I think, have relevance to trying to improve the sustainability of the built environment. Okay, so our first case study is an example of looking at, is it better to renovate or build a new building from scratch? You can see from the right there, this be careful what you wish, be careful what you wish for, and always look at trusted tradesmen. Right, so this study is looking at a large red brick building in the US that has been renovated for office use. Now, I have to hold my hand up that before I read this paper, I used retrofit and renovate as interchangeable. And the author of this paper would tut a little bit. Both of these fall under adaptive reuse of existing buildings, but the authors would distinguish that retrofit involves the addition to a building to improve its efficiency, whereas renovation involves modifications, improvements, alterations to an existing building to make to ensure it reaches a minimum viable standard in terms of occupational comfort or energy or thermal characteristics. Now, in terms of renovation versus new build, an important thing to consider, and we'll be talking a little bit more about this later, is the circular economy principle, which basically says, okay, if you're trying, it's ideally we want to try to source materials of low impact as possible. And so therefore, this study is only looking at the full life cycle of the newly sourced materials. Okay. So what this study is effectively doing is that it's looking at the impact of the renovation of this building, but also comparing it against a counterfactual, a imaginary building that is built from scratch. So this, the renovation work, which is based on an actual an actual renovated building, retains as much of the main structural components as possible: steel columns, beams, concrete, all the main important structural elements that really realistically, are, are very difficult to retrofit anyway. It looks at focusing on the environmental impacts of materials. So it compares the impact of sourcing new materials for the renovation. It, as we said, it doesn't include the entire life cycle of materials that are reused. These are materials that are effectively being provided with a minimal environmental impact, only the impact associated with things like maintenance, repair, replacement, reuse. So these are things that are included. We're not looking at virgin material for the renovation. We're basically saying, okay, if we're taking things that are pre-made, then we're not including the environmental impact of making it. As this study is then focusing on material choice, it also includes things like the impact of installation, demolition, and operational, the heating and cooling aspects. So these are excluded. So as we said, one of the choices in our life cycle assessment in terms of our boundary is, well, what are we actually really interested in? If we're really just interested in the impact of material substitution or renovation, then let's just focus on the impacts of sourcing the material. Okay, that doesn't mean that renovation won't have any new components. It will, and where renovation includes new components, the whole life cycle impact of producing the new stuff is included. So just to summarize, the new construction, completely new; renovation, mostly pre-existing stuff that has a reduced embodied impact that only incorporates the impact associated with renovation, and some new stuff that will have some new material that will have an entire cradle to grave or cradle to cradle environmental impact. Okay, well, what do the results say? Okay, so the figure on the left shows us the impacts associated with the renovation option, and you might look slightly familiar for those of us who have been looking at the previous slides. So this is the example we've shown previously for our interpretation, and the figure on the right demonstrates for the same environmental impact categories the determinants of the impact associated with new build. So these are all the relative contribution of different stages. And we can see some similarities, but some important differences. Most of the impact for the renovation option is based around finishes, or things like the opening glazing, things that aren't necessarily hugely structural, which is what you'd expect. Whereas if we incorporate the new build or hypothetical building that we are starting from scratch, we can see that the requirement to produce metal masonry structural components is much, in most cases, a much greater contributor to the overall impact than those associated with finishes, glazing, moisture protection, and plastic and composites, which is not surprising. But what does this mean for our environmental impact? Well, if we just look at the relative environmental impact across the same environmental impact categories, we can see that the renovation option, unsurprisingly, has a much lower environmental impact across all commodities or all impact categories, but this reduction isn't equivalent. Interestingly, we see that even though the mass is only 1/10, that same relative change is not expressed in terms of the environmental impacts. So the relative difference between the environmental impact of these two options is slightly lower than the reduction in material use associated with renovating as opposed to building from scratch. Now, what that effectively means is that the renovation phase itself involves lots of different impacts. It involves will involve environmental burdens, will involve energy. The renovation option is not without impact. So it reminds us that even though we might we might see occasionally phrases like sustainable or low impact or net zero being used somewhat interchangeably, even very environmentally benign options are actually not that environmentally benign. Okay, so the next case study moves away from issues of renovation to choice of materials. So one of the things I'm really interested in, partially because I'm also involved in a lot of studies on environmental impact of agricultural systems, is novel earthen or bio-based materials, partially because these are often outputs or co-products or residues or even wastes of other processes, including agriculture or construction materials. These sorts of materials often have high thermal inertia, they have good structural compression, they have a natural resistance to fungus, although this can be this can be very location specific. In my alma mater, which is built on the through which the largest river in the British Isles flows, provides has an on-site riverbank which is used for a source of sand, and unfortunately, this particular sand also had a particular fungus in it that quite liked the what I think it was magnesium in the concrete mix, and it started to grow through the concrete of new buildings. So that was an example of being careful where you source your materials. But earthen and bio-based materials also have good hygrothermal properties. So this is the flow of moisture and heat through materials. However, these are very underrepresented in building codes and are often very difficult to get through the planning process. I don't know if any of you watch Grand Designs, but a really interesting example is using a earthen shell or a burrowed house, which is effectively a big earthen mass over a house, kind of like a hobbit house, as a way of trying to increase its insulation properties. So this particular study is based around the incorporation of different bio-based materials and earthen source materials into a wall system, whereby the results are expressed in terms of a square meter. And these are compared with more conventional designs, including timber frame, insulated and uninsulated mason concrete. So this is just an overview of the design. We can see they have different thicknesses. And also interesting for those of us unaware, cob is a very, very old material that has been used for many centuries. It's effectively a mix of clay and earth with fibrous material. It's the oldest existing house in France, if I'm not mistaken, is made of cob. So this demonstrates the different designs are reflected by this study. So again, as we said, the choice of activities and stages that are included or excluded are really informed by what our study is interested in. So this study is interested in sourcing materials. It's looking at things like extraction of materials, processing it, transporting it, and it's interested in their relationship between those materials and the thermal comfort of the building. So it excludes the impacts associated with demolition recycling and the energy associated with construction. So no drills. It makes assumptions on the functional life, 50 years, and for things like plastering of biomaterials, bio-based walls, it has a maintenance assumption of once every 10 years. Why this is interesting is that it demonstrates the interaction between two different economic sectors. So, for example, we can see the impact of producing straw incorporates things like the burden by producing and applying fertilizers. So normally, these sort of impacts would not have any relevance to building design or construction, but by incorporating the design, by incorporating these bio based materials into design, we can identify the impact of interactions between the building and other sectors such as agronomic and agriculture. So what did the results tell us? Well, perhaps not terribly surprising. So these results are two global impacts. So energy demand and global climate change are kind of, as we discussed, relevant to global problems, whereas acidification and particulates are more local. And in all cases, the more established buildings, the insulated wood frame, the concrete masonry units, the insulated concrete masonry units have higher energy and demand and have higher impacts. The relative performance of the different bio-based, I should say, this is embodied emissions, this is embodied impact, this is just in the impact of producing 1 square meter of wall space. But the relative performance of the different bio-based options will vary across these different metrics. Now, as we discussed, one of the benefits of this type of study is trying to identify the impact of operational versus embodied impacts. So if we look at the impact of these different construction options on the actual heating cooling demand of this building, we can see that this actually varies quite a bit based on location, which is what you'd expect. A lot of cooling required in a desert situation, not so much in a temperate. In all cases, we can see that, well, in most cases, the light straw option performs slightly better. But what is interesting is that we can see that in some cases there is a trade-off, or at least a reduced embodied impact comes at the cost of a slightly higher operational impact. So, for example, in the case of the desert option, the reinforced earth has a lower environmental impact in terms of CO2 equivalent compared with compared with our conventional buildings, but still the reduction in the embodied impact is sufficient for it to have a lower overall impact. So some of these materials will have a lower embodied impact, but a slightly higher operational, even though the overall comparative impact seems to be quite persuasive. Now, you're probably saying, well, hang on, in the previous study, we for this house, we saw a very low, a much greater contribution for operational in our whole building example. Well, bearing in mind, this is a different building. This was just looking at wall space, and it's looking at a different functional life. It's looking at 50 years rather than 60. So the results here are not directly comparable with other results. Okay, so okay, I'm just going to speed up a little bit. So our next case study is looking at energy sourcing. And this study compares the impact of providing 1 unit of thermal energy based on different heat pumps as opposed to a conventional natural gas boiler. So what this results, just very briefly, a natural gas boiler, not a heat pump is similar technology that we see in our fridge. And in effect, what it does is that it takes a refrigerant, which is heated by ambient temperature, and that is then turned into a gas. It is compressed, and its heat increases, and this heat can then be used to heat water or heat spaces. Now, that in effect might sound like it's contravening the laws of thermodynamics, but it doesn't, because we're applying a lot of electricity to compress and flow and power the fans. So in effect, it's another way of converting electrical energy to thermal energy, helped with ambient energy sources. So this study looks at comparing 1 kWh of heat based on different types of heat pumps and the natural gas boiler. And it's expressed in terms of all these different impact categories. And first and foremost, we can see that in terms of climate change, both the heat pumps perform much better than the natural gas boiler, which is perhaps unsurprising. However, for many other impact categories, including freshwater ecotoxicity, the impacts are this insight is reversed. The ground source heat pumps actually perform worse. And partially this is due to the impact of a large amount of offshore wind in the grid, the national grid, bearing in mind that heat pumps require a large amount of electricity to run, as opposed to gas boilers. So what that means is this comparison might be sensitive to the level of gas and renewables in our electricity system. So this study undertook a series of scenarios that tried to say, okay, in the future, we hope we'll have much less gas, much more wind. What does that mean for our relative comparison of different impact categories? And what that means is, so this diagram on the right demonstrates the relative change of these impacts across our three different scenarios for the air source heat pump on the left, ground source heat pump in the middle, and the natural gas boiler at the end. So all of these cases result in a significant reduction in the impact for most impact categories, except for freshwater toxicity and metal depletion based on, well, the amount of wind that's used, as we said. So increasing wind would actually increase the metal required to sustain the grid and increase the freshwater toxicity impact. However, the relative benefit of these are across the heat pumps are much higher than those derived or as those foreseen for natural gas boiler. So again, the extent to which a natural gas boiler and heat pumps will have trade-offs is itself dependent on what's happening to the energy system, as opposed to not as well as what is the efficiency at the level of the individual settlement or building itself. Okay, so we're on to our last case study. I remember we talked a little bit earlier about the potential benefits of reuse versus recycling. Well, we're looking at a situation where if we are serious about incorporating circular economy principles, we need to understand that recycling itself is actually quite an environmentally intensive process in many cases, particularly for materials like steel or aluminium. If we are trying to undertake a circular economy paradigm, we need to try to really be serious about replacing the waste pyramid paradigm with something a little bit more dynamic, or at least reflects that it's ideally better to design something so it's not it requires as few materials as possible, that it's better to reuse than remanufacture, that it's better to remanufacture than to recycle. But this choice of recycling versus reusing versus remanufacture will have economic as well as environmental costs. Life cycle costing is a method that is similar to life cycle assessment, that follows the flows of revenues, of costs across the system to try to identify, okay, can we compare the environmental impact of two options with the eventual economic returns? So what this study does is this particular study is looking at a building that has been partially demolished, leaving only a steel frame, 114 tons of it. And this study is trying to identify, well, okay, this steel is a resource. It's something that's going to generate a revenue. But is it better to generate this revenue from reusing it as opposed to recycling it? And how does this benefit compare with the environmental impact? So we can see that recycling and reuse, if we start at the same or comparable points, the demolition or deconstruction, actually has different materials or rather different stages, different technologies, different processes involved. In particular, the recycling process through the use of perhaps electric arc furnace or other steel mill processes requires a lot more energy, whereas reuse will incorporate things like different assumptions on the how material is recovered and how it's cleaned. And so in comparing these different stages for our 114 tons of steel, we can see that the reuse presents a lower environmental impact, but not significantly lower. And the difference is actually quite smaller than the large error bars, at least for CO2. So even though reuse is better, this study at least suggests and reminds us that reusing something is not it does have its own environmental impact. What does that mean in terms of costs? Well, okay, the costs actually are quite similar. So the costs here are associated with the labor associated with construction, demolition, and also the environmental costs associated with human remediation impacts associated with different pollutants, and of course, the costs that we get from selling steel that is recycled versus reused. But these, as we see, are vary quite significantly. Between minimum and maximum values for each of these estimates. So our single value here might potentially be misleading without a better understanding of how these dynamic elements can change our understanding of the relative benefits of reuse versus recycling. So if we compare some of these inputs, these assumptions, based on based on the highest or lowest assumption, we can see that the economic benefit of reuse is very much dependent on assumptions associated with labor costs, because reuse, dismantling, recovering is more labor intensive than recycling, at least through this study, and of course the value of reused steel. Whereas the extent to which recycling is more cost effective is based on the emission rates associated with different activities. And of course, also to a lesser extent, the emissions, the costs associated with emissions themselves. Okay, so we're coming to the end. I'll try to speed on. So what kind of insights can we derive from these kind of studies? Well, we've seen that if we extend our estimate to include non-CO2 emissions, that win-wins are actually quite difficult. Very often we see trade-offs between global and local pollutants. Reuse itself, while very likely to have environmental benefit, still has a inherent environmental burden with it. So the benefit is relative. The benefit can be considered relative to an alternative in which the material was not reused. Isolated estimates don't really help us all that much. It's really important to be able to compare our results with something, either an alternative or some other study that looks at similar studies. And that, of course, embodied results are not separate to operational issues. We saw in the impact of different wall materials that the choice of less embodied materials with less embodied impacts might actually result in a slightly higher operational energy demand. And the extent to which some of these choices uh, may have a greater or lesser environmental impact will depend on what's happening around the overall system, beyond what's happening within the actual building itself. So life cycle assessment has a number of different strengths. The biggest strength is that if you look across the entire life cycle, it doesn't allow one impact to trade off one another. If you reduce your impact in one stage but increase it in another, that will be evident by looking at the contribution of different hotspots. It provides a holistic view of environmental impacts by allowing us to look at both global impacts, local impacts, and material use. It allows us to look at the inclusion of novel materials that might not necessarily be represented or hypothetical scenarios. Of course, there's a number of different limitations. It depends on a lot of assumptions and is really, as we said, only useful as a comparative tool. The studies will have different scopes. So one study may leave some impacts that are may omit certain impacts or stages that are included in others. So very often we need, even though we need to compare, it's really only better to compare different alternatives within the similar study. Really, one of the things that we need to do as well is understand this life cycle assessment in isolation is not as useful. We often need additional tools like, for example, modeling the thermal properties of a building or modeling the impact of different consumer needs on the thermal requirements of a building in order for us to actually generate the data input that we need for life cycle assessment. And well, not necessarily a limitation, but it's important that we don't confuse the benefits of relative and absolute impacts. So we can identify that something might have an impact per kg. So a steel mill might have a particular impact per ton of steel, but it might produce it will likely produce a great many tons of steel during the course of its functional life, which have a very important impact on the absolute limits on the receiving carrying capacity of the local environment in terms of nutrient loading or other impacts. So even though something might be very efficient per kg of metal, the overall impacts are also very important. So to conclude, life cycle assessment is a powerful tool. It can help us compare different options for providing a good or service. However, results are really only meaningful by way of comparison, either within or amongst different studies. It can help us inform different decisions in the built environment. We looked at decisions around reuse, renovation, material choice, home heating choice, and the economic benefits associated with use versus recycling. However, the uncertainty associated with these really means that primary data is so valuable, and unfortunately, this is often hard to come by. And this is also evident by the high uncertainty associated with some of our estimates, like we saw in our error bars. This means that we need to have a very clear choice of exactly what we need to measure, what we need to include, and omit those that aren't relevant to our research question. Okay, thank you. Sorry, I'm a little bit longer than expected. Here are our references. I'm happy for any questions.
Right, as it stands, we don't have any questions in the chat yet.
That's okay. That's fine.
So while everyone's thinking of what those questions might be, I actually wrote down two, but you might consider me nasty and say I want to take you for coffee rather than do it here. First one is around, you looked at the comparison renovation retrofit versus new build.
Yes.
And I wasn't sure if in the new build there was a consideration of the fact that you actually have to demolish the old building before you can start doing that, because I would assume that that demolition is going to have a number of impacts as well.
That's a very good point. That was one of the alternative kind of case studies in this study, but they only quantified the results associated with the new build. So, but again, it kind of depends on your boundaries. So that study, even though it identified that this is something that could be included, one of the points that this study highlighted was that you can come up with alternative boundaries that are equally justifiable, but will incorporate different activities. So obviously, if you're starting off a building that has different characteristics, then your boundary is different from, let's say, a greenfield site, and you'll be incorporating different demolition and construction activities than construction activities. So that's a very good question. The point at which you draw a boundary around some of these kind of studies is actually a real bone of contention, and you'll have different conceptions and different studies will say, "Oh, you should start here," and "No, you should start here."
Yeah, and then the second one for me was around looking at your different mechanisms of construction. So you cop all the way up to your insulated concrete. What I found interesting was that obviously there's the impact of the materials. There's quite a bit of an impact based on heating and cooling aspects.
Yep.
And then looking at where it is located as a building. Considering that if we go back a few hundred years, we used to build with local building materials. And I was actually wondering if there's a relationship between the locality of the building materials that we used to use and how good they were suited for the climate in which we were using them, versus our current approach of using the same building materials everywhere.
I would assume so. So things like cob will have different hydrothermal properties than earthen walls, or so presumably, through trial and error over many centuries, it would become clear as to, given the now again, it would the extent to which you builders at the time or would be aware this was obviously being formed by the functional life of the building. If you're building something that's very short, that's only intended to be short-lived anyway, the relative benefits might not be as necessarily obvious. But you would presume that, considering these materials were in use for many, in some cases centuries, that there is that just by definition of based on what is recognized as providing a certain level of comfort, would select for these sort of materials. Regardless of what century you're in, we have humans have a certain thermal profile in which we're more comfortable, beyond which we're slightly less comfortable. That doesn't change whether you're in 15th century France or 21st century Medway. So one thing I would also add is that presumably this sort of decision is also influenced by what material is available. Certain things like cob, I presume, could be produced pretty much universally, whereas other materials might be more specific. So where I'm from in Ireland, we have there is a very specific ancient technique that's based on reed construction, with some earthenware around it, a kind of a variant of wattle and daub, but using reeds rather than, and this was something that was intended to be basically replaced wholesale every 2 or 3 years. But mud and reeds are easy to come by.
Brilliant, thank you. Over to the others. Beverly is typing away. I'm not sure if there's any question coming. Mark, any questions? Bernard?
No questions from me. So it's all very informative, and a lot of it bamboozling as to how we can sort of translate that easily, I suppose, into our own retrofit processes. Sort of like the other day when I attended the session in Tunbridge Wells, it was my property hasn't got any cavity wall insulation. I was going to go and get someone to inject all of that. Those sort of throw me there into a whim. Said, no, don't do that. No, go for cork instead. That was like a nice, easy advice, which is now sort of, obviously with this, I'm not planning on demolishing the house, but you know, it was now sort of some other sort of quick wins maybe, but yeah, it certainly more food for thought,
Sure.
I think, rather than things
I
that
mean,
put into action.
Yeah, absolutely. I you know, prizes for the most obvious statement, but you know, one of the things that often is neglected in these sort of stories, they assume a house that is moderately well insulated, which in many cases is not the case. So one of the critiques I have around these studies is that they reflect a slightly idealized version of reality, whereupon the benefits of this technology or this heating option is ignores other very important low-hanging fruits. Not that, you know, not that, you know, significantly improving your insulation is easy or cheap. It's not. And as you said, the options for that might be limited depending on the type of construction. But these sort of studies, I think, often have a somewhat idealized version of reality. So I'm not necessarily, I'm not saying you shouldn't go out and buy a heat pump, although my partner's mother-in-law is very, very, very angry with her heat pump, but that's another story. But I'm saying that, you know, if you're considering looking at a heat pump, then also have a look at your insulation as well.
Yeah. Thank you.
Thanks, Conor. We have a question from
Oh,
Beverly. So,
brilliant. Hello. Let me see. Okay, so there will be a difference between industrial commercial construction and the mechanical techniques and DIY processes. Okay, so very good question. How does LCA manage to assess this? So it manages to assess this at two different stages. So it'll reflect this in terms of the types of materials that are incorporated. So different materials will have different embodied energies, will have different impacts. It'll cost more energy to produce this rather than this. There we go, showing my lunch. Or it might be sourced from different locations. So we saw the study that looked at different alternative materials had different transport choices. So materials like cob or earthenware might be capable of being sourced relatively local. Now again, you know, your mileage will definitely vary. But it also will reflect it in terms of the construction process. So if you're building something mostly out of steel, you need to include a lot of welding. If you're doing timber framed, it might be more drills or other elements. So by comparing the type of processes that actually go into the construction and what those processes need, you can try to reflect what different materials actually, either both how they're made, but also how they need to be treated or processed in the construction process. One thing I am very interested in is because a lot of these things like home DIY will have an impact on or how well a boiler is maintained will have a big impact. And things like poorly fitted windows, my flat, I'll hold my hand up, it's not great. These sort of things often might have a very small, might have a marginal impact, let's say, per, you know, on a daily basis, but aggregated over the course of the functional life of a building can be quite significant. And the things that are very small, that have a relatively small impact per day, are often ignored. So like the DIY processes, what's the life cycle benefit of actually knowing how to maintain your boiler and knowing how to ensure your windows are properly fitted is something that I would be very interested in looking at. I haven't seen it in these studies, but it's the type of thing that the little small, achievable, well, readily achievable actions, what their benefits could be, is something that I would be very interested in, just from a purely academic perspective. I'm sorry, Beverly, I don't know if I've answered your question. If not, please put your oar in.
I mean, that's fine. There's lots of different things to think about there, and what you were talking about, the sort of the boilers and the windows, and I know we focused on, well, not focused, but we spoke about that yesterday as well. You're absolutely correct. They are so small, and also for the DIY man, I'm not saying that I do a lot of DIY, but I do try. I would call a specialist in and assume they know what they're doing. But thank you, Vim. I now know not necessarily that may not be the case. So over time, what would be the impact on, the house that I just, made sure that I'd done the insulation. Yes, I have got little P's at the moment, but I'm looking at other things now. I don't know what those small differences or those small implications will have over a length of time.
Well, that's a really good point, and that's one of the reasons why the whole building life cycle assessment is a really, really important and a really potentially useful way of taking this kind of usually static model and actually turning it into something that reflects changes over time, which are going to happen. The one thing that's not going to be, the one thing we're not going to have is a static situation. There will be change, definitely.
Lovely, thank you. Thanks for that. Lots of food for thought. Food for thought.
So no, it doesn't appear that we have any other questions. Then I think that does bring us to the end of this evening's event. I hope you have found it useful. I think you've done a fantastic job, Conor, of trying to explain and break down a very complex topic. And to kind of pinch Mark and Beverly's phrase there, I hope it has given you all some food for thought and to start thinking around life cycle assessments. Thank you, Wim, for popping a quick link in the chat for you all. So we are really keen to get your feedback on today's session. It's really important to us. It will help us inform kind of how we can take this next sort of piece of work forward and partnership forward. I really just like to thank you all for joining us, for taking the time to submit your questions, and hope that you'll join me also to thank Dr. Walsh for delivering this evening's really insightful talk. We'll hold on maybe for a couple of moments. Yeah, thank you, Beverly. Just so that you've got the time to click on that link. Maybe just give me the thumbs up once you've accessed it and you're in there. But really, that just leaves me to say thank you, good luck with the next steps of your home sustainability journey, and enjoy the rest of your evening. So thank you all.
Thanks very much. Bye.
Thank you all.
Take care. Good night.
Thank you.
They're all gone. Thank you, Conor.
Shall we stop?
Do you want to stop recording? Yeah.